Okay, so our next speaker of the session is Glitta Cheeran from Jena, who will talk about the impact of linear information forwarding on the learning performance of nonlinear fiber-based extreme learning machines. So please, Glitta, go ahead.
All right, thank you for the introduction. So I'm Glitta. I am from Mario Chemnitz's group in Leibniz IPHT Jena, and I'm aware that I have a long title, but we will break it into chunks. So first we will have a recap on nonlinear fiber-based extreme learning machines, and then I will introduce the topic of linear information forwarding, and then in the end we will see the impact of the first on the other. So to start off with, this is what a basic setup would look like for fiber-based ELM. So we have a pulse laser with a femtosecond pulse. This is the information carrier. And you would have information, data like the MNIST handwritten digits, which would be encoded onto this pulse using a wave shaper or an SLM-based setup. And then this pulse that has the information would go through the highly nonlinear fiber, where there's frequency mixing. And at the output, you would have a supercontinuum. And from this output continuum, you would bin and do a linear regression and have the solution to your problem. In this case, for MNIST, it would be classification. Now, this is an extreme learning machine because we train only at the output layer, which is the supercontinuum. So let's take a look at that. So we have intensities spread across wavelengths. And the first thing we do is to select the wavelengths that are relevant. And then this would go into the linear regression where it's weighted and summed, and then you get the solution. Now, there are different ways you can do the bin selection. You can base it on statistics. So you can do variance filtering, for example. And there's also different groups that have done, for example, principal component analysis to select the appropriate wavelengths. But what's interesting is that the bins that are selected fall in the pump region, right? So why is information concentrated in the pump region? For this, I would like to take you on a journey along with information. For this, first, I will start with a smaller information. So not the whole MNIST, but just a singular bit, 1 nanometer small phase change. And I toned down the power also of the setup. So usually for the classification tasks, we use 500 watts to 1000 watts. But in our case, we tone it down to 250 to 300 watts peak power. And now in the pulse, which then goes to the wave shaper, inside it looks like this, where there is the Gaussian spectra of the pulse that first goes onto the grating, and then it would disperse, and from there it goes onto the liquid crystal on silica SLM, where you now have access to this to change in wavelength, either the amplitude or the phase. So in our case, we would apply the bit, which is the phase. Okay, wait a minute. Sorry. Yeah. All right, after this, we pass it through the highly nonlinear fiber, and then we get the supercontinuum, but there's something unexpected there. So this is not just a continuum, you also see a peak. And this is corresponding to the phase that we've given. So now we have 2 questions. What is this effect? And why is phase visible in intensity? Now, something interesting is that this has been observed before in the past 2 decades. And in our paper, which is available on arXiv, we explore this in theory, in simulation, and in experiment. So for now, we have been looking at it in the wavelength or in the spectral domain, but we will look at it also in the temporal domain. For this, we look at the spectrograms. So we look at the spectrogram of the laser. Here, as expected, there's the Gaussian profile of the pulse. So the transform would be also Gaussian. And what happens in the wave shaper when you apply the bit? At the output, they're both Gaussian. And as expected, phase wouldn't be visible. But something interesting that we see here is that this is also new to our group, right? We know that when we apply a rectangular filter, the transform of it, Fourier transform of it, would be a sinc function. And this applies the same for phase that is applied. So you see the transformation, and if the bit is small enough, it appears as a continuous wave background. And when this passes through the nonlinear fiber, this can be decomposed to 2 fields. So there's a strong field, A, and then there's the weak field, which is the continuous wave background. And the strong field A would experience cell-phase modulation and then also have cross-phase modulation on the weak field. And once it propagates, we see that the strong field experiences SPM, the phase is shifted, the weak field remains almost constant, and then they interfere, and that's how we see the peak. Now, what does the peak depend on? So in the theory, we see that it depends on two things. One is the nonlinear gain, and the other is the phase of the bit. We can now play around with this. We can try with the nonlinear gain, with the power. What happens when we increase the power? So far we have been in 300 watts peak power. In simulation, when we increase, the spectrum broadens, but the peak is preserved. And what happens when we play around with the phase? So at the central wavelength at 1550, I'm applying phase from 0 to pi, and we'll see what happens at the intensity. We see that the intensity increases with the phase for both the power cases. And to quantify this relation, we use Pearson correlation. So this is a quantity that goes from -1 to 1, and if the magnitude is 1, it means that it's linearly correlated. And we see that the correlation is nearly 1. And this is the case in simulation. Yeah. And in experiment, at weak power, we see a few modulations from cell phase modulation because we don't have a perfectly transformed limited pulse to begin with, but we see the peak appearing. But when we increase the power, and we do this by introducing an EDFA in the setup before the wave shaper, the peak disappears. But what's interesting is that the relation between the input phase and the output intensity remains the same. Now, that was the case of a singular bit. What happens when we encode the whole MNIST? So we start with the spectra, and we have to encode now a two-dimensional image. But if you remember, in the wave shaper, we only have access to one dimension. So for this, we flatten out the image, and then we apply it as phase onto the spectra. And after the nonlinear propagation, what's interesting is you can see the peaks corresponding to all of the input that you've given. And this is also the case for experiment. Even though there's modulations on the side, you see the peaks corresponding to the information. Now, what's interesting is you can now do the opposite of what you did to the wave shaper. So we flattened out the 2D image. We can now just slice out the spectra and recover the images directly from the intensity. To note here, there is a little bit of fading out at the edges. This is because of the Gaussian profile. And in the experiment, it looks pixelated because we have downsampled the image. We can also do this pulse to pulse. So instead of the spectrum analyzer, if we use a time stretch technique, we can then get pulses. And in each pulse, if we zoom into one, we also see the peaks there. We can recover images from this as well. It's a little distorted, but when we see the average recovery of the images, so from 200 pulses, when you average, you see that they look the same. And there's a standard deviation, which is around 1% of the dynamic range. Now, to answer, to answer the questions, why is information concentrated in the pump region? And what is this effect? And why is phase visible in intensity? The answer is Kerr-induced inline interference. And because of this, we see that input phase is revealed at the same wavelength in the output intensity, and the relation is correlated linearly. Now, what's the impact of this in learning performance? Okay, I don't know what's happening, sorry. Is there a way to stop this from... Okay. So we start with the MNIST dataset that's cropped, and we use 2,400 samples for training and 600 for testing. And when we look at, when we look at the classification accuracy for just the raw pixels, we see it's 80.4%. And if we look at just the encoding wavelengths that we've used, the intensities, and we do the linear regression on those, we see an improvement to the accuracy. And if we look at just the encoding region and use a bin selection technique and use just 100 spectral bins, the performance almost the same. And if we use the entire spectra and we check for the accuracy, we see that there's a marginal change there. Now, this is, because the slides are going on its own, you can see here, this is actually a function of the task that we've used, right? So MNIST itself is not a very nonlinear task. So we can use this linear regime, right, at low power to classify this. And you don't see much of an improvement with nonlinearity added on top. Now, for summary, so we saw linear information forwarding, and we were able to quantify it using Pearson correlation, but there's also nonlinear information that's being forwarded. And how can we quantify this? To know more about this, you can check out Juliana's poster. We also saw that information is concentrated at the encoding region. And how can we effectively select now wavelength pins for the tasks that we use? To know more about this, check out Mehmet's poster. And we see that weak nonlinearity is sufficient for tasks like MNIST classification. But when does nonlinearity improve computation? For this, check out Sophie's poster. I would like to thank my team, the collaborators and the funders, and thank you all for your attention.
We have plenty of time for questions, so who wants to go first?
Yeah, I wonder if you tried, or maybe this is a suggestion more than a question, done things along these lines, but then often we concatenated the actual images and nonlinear transformation done by the fiber. So the question is whether it helps. In other words, you still have the images, right? And then the classifier can classify those. And then adding additional pixels with the nonlinear transformation usually helps quite a bit.
I'm not sure I understood the question. So is it, a suggestion, yeah.
Okay, so you could take the images, in this case the MNIST, feed them to the linear classifier. Or you can take independently what comes out of the spectrum going through the fiber. Or you can take both.
Yeah.
And it's interesting to see how much it helps to add the nonlinear.
That's what this slide was about. So the raw images with linear regression gives the 80.4%, and then just using the intensities that come from after the propagation, it goes to 85.
Not independently, but at the same time, you concatenate them.
Okay. Oh. Okay, should try it, yeah.
Normally it should be better.
Thank you. Any more questions for our speaker? I do have one. What is the material that you're using that has that much nonlinearity? I know I always ask the same question, but...
Sorry?
So what material is your system made of that has so much nonlinearity?
We're using highly nonlinear fibers, yeah.
But what are they made of?
Silica.
Silicon.
Yeah.
Okay, so... Next one I bring, sorry.
All right, so I mean, this slide already shows one notable concern, that you're doing this on a data set that is 2D, and your system is inherently 1D, right? Like it's. Have you seen any do you have any way that you can encode this data into that 1D system that doesn't have the 2D structure, right? Could you, for example, multiply it by a random matrix before you encode it or something? Have you tried that?
No, I have not tried that, no.
Have you seen evidence that that there's only short-range coupling taking place here?
I'm not sure I understood the question. Could you repeat it? Yeah.
So when you encode any given piece of information into this field,
Yeah.
right? It's not necessarily going to have strong coupling to every other part of the spectrum. It'll be somewhat local.
Yeah.
But here you're unwrapping this two-dimensional thing into one dimension, so the natural sense of locality is changed.
Yeah.
So I'm asking, have you seen any evidence for that, or have you tried
Have not
anything
tried
to
it.
get?
No.
All right.
It's supposed to be very fluffy, but so if the next speaker wants to already start setting up, if there are no more questions.